So we've been looking at double integrals, which is essentially the volume underneath a function over some region D, right? I mean, there's the notation. You've got some region D down here in the xy plane. You've got some function defined up above, and you're looking at whatever this is up above here, and the volume in between there. Now I say volume, but it's in quotes, right? Because if the function value is negative, then you're going to take the height as negative, and some volume might cancel out, or you might end up with negative volume or whatever. But that's fine. It's a double integral of a function over a region. Now sometimes it's going to be more convenient for us to do this in polar coordinates, either because the function is more easily expressible in polar coordinates, or usually it's because the domain is more easily expressible in terms of polar coordinates. So the idea is you're going to, let's look at the xy plane, although maybe I'm thinking of it in polar coordinates now, and you've got your region D, here's x and y. And before, what we did was we took the region and we chopped it up into a bunch of little rectangles, right? Well, now I want to think about it as chopping it up in little polar rectangles, so to speak. Essentially, each rectangle here was a dx in one direction by a dy. Well, my variables are now going to be r and theta, so I'm going to look at this in terms of cutting it up into, cutting the theta up into a bunch of pieces and cutting r up into a bunch of pieces. So essentially it's a polar grid here, just like we had xy grid over there. You've got radial lines from the center, and you've got circular arcs, all concentric with the center as this, with the origin as the center of the circle. And so what I need here is each one of these little pieces now has a little bit of area. You take that area and multiply it by the height function, and to get a little bit of volume. Right? It's the same idea as before. It's just the dA now is not a rectangle, it's kind of a little polar rectangle. And what I need to figure out is how much area is there here. Once I know that, of course, I'm going to take my 1 point, plug it into the function to get the height, so I can calculate volume. But anyway, what is that little bit of area? So I'm going to redraw that. What I have a little bit of change in theta, d theta there, and I've got a little bit of change in r right here, let's say dr. Okay. What's the area? Well, there's different ways to do this, but essentially with dr and d theta small, I'm looking at that thinking, well, it's practically a rectangle. And the area of a rectangle is length times width. Width is dr. I just need to know how long that is across. Well, that really depends on how far away from the center here you are. Right? The same little dr, if I put it down here, only makes a little bit of area, or if I put it, way out here, it makes a lot of area. So this dA now, this little bit of area, is going to depend not only on dr and d theta, but actually how far away from the center you are. So that's distance r. Okay. Well, if you know the radius of a circle and you know an angle, then you can calculate the arc length. That arc length is r times dr. No, it isn't. It's r times d theta. Right? Well, it's the radius times the angle. That's the arc length. My angle here is d theta. So the area now, the area of that little piece, dA, is length times width. So this is r d theta dr, or it's r dr d theta. That's the area element in polar coordinates, r dr d theta. Essentially, I mean, there's another way to look at this too, in that you have two planes that you're working with. You have the r theta plane and you have the xy plane. And little rectangles in the r theta plane get turned into these circular rectangles, so to speak, right? They get bent. So this is r between some starting point and some ending point, some little dr there, and theta from some starting value to some ending value, some d theta there. That little rectangle in the r theta plane gets bent into um, um, a, into a bent rectangle here, sort of circular wedge um, in the xy plane. And depending on where it is, um, determines the area. I mean, this same rectangle here or here, right? That's my two examples here and there. Give me different different areas in these two different places. Likewise, this one out here would be this thing. It's the same change in theta and the change in r, but it's placed differently in the xy plane, and so the area element here, the little dA, has that extra r in it to determine where this rectangle is actually being mapped to in the xy plane. Okay, so what's going to happen is we're going to have these double integrals in x's and y's, and then you convert them to polar coordinates. You've got to convert both the function and the area element. Well, the function's easy enough to convert because the conversion between polar coordinates and rectangular coordinates, if you don't remember it, here's the picture, right? Every point in the plane has both an xy coordinate and an r theta coordinate. Well, x and y are determined by horizontal and vertical distance from the origin to get to this point, right? Move over x, go up y, right? R and theta are the straight line distance, that's r, and theta is the angle measured in a counterclockwise direction from the x-axis here. So now trig tells us what our relationships are. X is equal to r cosine theta, and y is equal to r sine theta. So when I'm converting this thing, this is f of x comma y. Well, x is r cos theta, and y is r sine theta. And then dA is r dr d theta. Could be dr d theta or d theta dr. Usually, because we generally write polar functions where we have r as a function of theta, not theta as a function of r. So because we write them that way, generally people see it easier with that as dr d theta. Let me do an example here. Let's find the volume of how about a sphere of radius 2. So I'm thinking of x squared plus y squared plus z squared equals 2. And the way I'm going to calculate that is I'm thinking of the sphere centered at the origin. Well, I mean, it is centered at the origin. But I'm just going to say, let's take a look at the region here in the first, just for positive x's and y's, and just find the volume there, and then multiply by 8. Right? So volume is going to be 8 times the double integral of the height function here. Well, the height function is the square root of 2 minus x squared minus y squared dA, and we're going to integrate over this region D here. Okay. Now, the thing is that region in the xy plane, let me just look at the xy plane here, x and y. Sorry, this was supposed to have radius 2, so this should probably be a 2 squared, shouldn't it? Yeah, you probably caught that already. There we go. Let's make that a 4. So this is a 2, right? I could say x goes from 0 to 2 and y goes from 0 up to the square root of whatever that is. However, if I do in polar coordinates, this is just um, theta equals 0 up to theta equals pi over 2. So if I look at it this way instead, I'm going to do this as, instead of dx dy or dy dx, I'm going to do this as r dr d theta. The theta is going from 0 to pi over 2. And for every value of theta in between, I look at that and say, well, r goes from 0 out to 2. This is actually a rectangular region in polar coordinates. That's just the limits of integration here are constants. Converting this function now, this is the square root of 4. Actually, if I factor minus 1 out of that, that's 4 minus x squared plus y squared. And there is also a conversion up here that I didn't write down, but x squared plus y squared is r squared. So when I see those things, I'm inclined to do that. So this is that. Think about trying to integrate this either with respect to x or with respect to y. You can do it. It's a pain in the neck. It's a trig substitution. But now we convert to polar coordinates and voila, look at what we have. We have this thing. First of all, it is a rectangular region, 0, constants on the integration. It's a function of r times a function of theta. So I'm actually going to split this apart. This is the integral of 8. Sorry, this is 8 times the integral from 0 to pi over 2 of d theta times the integral from 0 to 2 of r times the square root of 4 minus r squared dr. This one's just pi over 2, so I've got 8 times pi over 2. And this one is a u substitution with u equals 4 minus r squared. Du is minus 2r dr. I've got the r dr, so I'm going to have square root of u, so I'm going to integral the square root of u times du over negative 2. So we've got 4 pi times, this is going to be a u to the 3/2 times 2/3. I still got this times 1 over negative 2, and evaluate between somewhere and somewhere else. The 2's cancel out. I've got a 4 pi over 3, actually negative, and then I've got u, which is 4 minus r squared to the 3/2 power, evaluated between 0 and 2. So here we go, negative 4 pi over 3, plug the 2 in, 4 minus 4 to the 3/2, plug the 0 in, 4 minus 0 to the 3/2. Yay, I like that. So I've got, because the minus sign was kind of worrying me, but I think we're okay now. I've got 4 pi over 3 times 8, because 4 to the half power would be 2, and then cube that, so that's 8. So times 8, so I've got 32 pi over 3. And I think, you know what, I'm pretty happy with that answer, because I happen to know from previous life that the volume is 4/3 pi r cubed, and so this should be 4/3 pi times 2 cubed, and look at that. That's what we got. Okay, so there is the volume of a sphere calculated with a double integral in polar coordinates.